Here's an example for our indeterminate powers. So we're going to do the limit as x goes to 0 from the right of x raised to the square root x. And this is an indeterminate power. We see x's in both the top and the bottom here. And let's actually check it out. So what is this base term doing? Well, that's getting closer to 0. And what is our exponent doing? The exponent here is also, square root x is also getting closer to 0. So our exponent term is getting closer to 0. Our base term of this power expression is getting closer to 0. So we have that 0 raised to the 0 form. So when the base term gets close to 0, it wants to make the whole expression get close to 0. But when the exponent gets close to 0, it wants to make the whole expression closer to 1. So there's this kind of competition between our base, which wants to make the whole expression 0, and our exponent, which wants to make everything 1 or get closer to 1. So there's kind of a competition here. All right, so how are we going to do this? And we've dealt with these types of functions before where we have variables in both the base term and the exponent. And the way where we saw them was when we learned how to do logarithmic differentiation. So it's going to feel what we're going to do here, how to actually calculate this limit. And this is true for our indeterminate powers. It's going to kind of take a lot of the strategy from that logarithmic differentiation technique that we saw. And so we have our steps outlined over here. Let's start with step 1. And let's start by just writing our function. We're going to call it y. And we're going to say y is equal to x raised to the square root x. Leave a little space right here. And that's because in step 1, we're going to apply the natural log function to both sides of this equation. Why do we do that? Well, we've seen before, log function has a good way of dealing with exponents. And so that's the second step, is to simplify this right-hand side. So this square root x, since it's an exponent on everything inside the log function, we can actually bring this down and in front of the log function. That's one of our special log properties. So we can simplify this right-hand side. And the log property said that the natural log of b raised to the power r is equal to r times the natural log of b. So that's just one of our special log properties. And that's what we did here. We took this exponent, brought it down, put it in front of the log. All right, so now we're going to calculate the limit of this expression. That's step 3. So we're going to do the limit of natural log y as x approaches 0 from the right. And let's fill in what we know natural log y is. So it's square root x times natural log x. And that kind of looks familiar. Square root x times 0. What is that? Well, this term here is getting closer to 0. And this term here is getting closer to minus infinity. This was an indeterminate product. And we did this one. So there was a lot more work here. What did we find? We found that this limit was 0. Let's go back, just so you're not trying any sleight of hand here. We're doing the limit of square root x times natural log x, and we're seeing that it's an indeterminate product. We've done this one already, so we're not going to go through it again. What were the steps here? Where? Yeah, here we go. So this is where what did we do? We had this indeterminate product, and then we rewrote it kind of cleverly as a fraction, and then used L'Hopital's rule, and we went through a bunch of work and ended up with 0. So this was a previous example we did of calculating square root x times natural log x. All right, so let's go back to the one we're interested in. All right, so here we are. So no trickery here. We're doing the limit here, and we've previously seen this thing as 0. All right, so what are we going to do with this? Well, in step 4, so normally there's going to be more work in here, right? We're not going to go right from here to here normally. There's going to be some more work that has to be done, and we've kind of nicely already done that. All right, so once we have this, though, once we have our limit, now in step 4, we're going to actually use this kind of clever trick. So y is equal to e raised to the natural log of y. So we know e and natural log are inverse functions of each other, so they just cancel out. So all this is saying is that y is equal to y. But we're going to use this to help us calculate the limit of y. Let's see how. So we're going to do the limit of x raised to the square root x as x approaches 0 from the right. That's really what we're interested in. And if we remember back, we originally said, let's let y equal x raised to the square root x. And then we applied natural log to both sides. So this x raised to the square root x, that's just y. And now we use that trick, that y is also equal to e raised to the natural log of y. Okay. And then e is a continuous function. This exponential function is continuous, so we can actually bring the limit inside this exponential function and bring the limit right on into the exponent there. And the reason why is because the exponential function is continuous. And continuous functions work nicely with limits. We can bring the limit inside that continuous function. And so then we need to know, well, what's the limit of natural log y? And just so happens in step 3, that's what we calculated. We calculated the limit of natural log y. We found it was 0. So we end up with e raised to the 0, which is just 1. Not too bad. Kind of a lot of tricks, though, in here. So, you know, these can be, we're using some natural log tricks. We might end up with an indeterminate product that we have to do something with. And that normally involves trying to rewrite it as a quotient and then use L'Hopital's rule. And then we're also using this trick of letting y equal e to the natural log y. So there's a little bit of subtlety in here. But this is the general kind of strategy for how to handle those indeterminate powers. All right, so that's going to be the last indeterminate form we look at. So we've kind of seen them all. Indeterminate quotients, 0 over 0, infinity over infinity. Indeterminate products, 0 times infinity. Indeterminate differences, infinity minus infinity. And then this whole slew of different indeterminate powers. 0 to the 0, infinity to the 0, and 1 to infinity. So a whole bunch of good indeterminate forms here. And the first step for all of these is just identifying what form you have. Identifying that's an actual indeterminate form. And then we have some different strategies from there. All right, so this is going to do it for our indeterminate limit section in L'Hopital's rule. So next time, we're going to get into more applications of derivatives. So we're starting to use derivatives in some of our work here. So we'll see some applications coming up soon. We'll see you then. Bye-bye.